Because most construction costs are high, die casting is economic only for mass production purposes. The process easily lends itself to automation, and in recent years there have been increasing developments in automation in the die casting operation to enhance even a higher productivity. Some examples of automation operation are metal melting, metal lathering, trimming and subsequent treatment, die spraying, die heating and cooling unit. Now let us take a look at the plant layout and process stages explained by Mr. Yeong Teow Poh, the plant manager.
This is our die casting manufacturing process. From raw aluminum, there is ingots and scraps. We are put into the melting furnace for melting. After the melting process is finished, we have a transport ladder to bring it to the holding furnace. But before that, we purify the metal by diecasting it. After diecasting, then we will pour it into the holding furnace. On the holding furnace, our process of die casting starts. Die casting, trimming is in one whole machine. After trimming, it drops into a conveyor. Conveyor will convey into a delivering unit. There is a vibrating unit. After that, it comes out from the dryer itself. Then the inspection and the packing people will inspect the part and pack it into the box. Then from there, our quality inspector will inspect the outgoing inspection by the AQM method. Then we will put on a shipping area where we will ship the part to our vendors for machining. And come to our layout. We have 3 melting furnaces over here. Each of them 800 kg. You can see over here is our aluminum ingots. Here is the return from all the machines with the runner and overflows. We are putting to melt. After melting, we have a forklift attached to a transport crucible. We bring it over here, and here we do our diecasting. After this, the forklift will bring the metal to either of the 5 machines, pour into the holding furnace. From there, we have a die casting machine with fume mat, auto spray, pig mat, trim press. This is our conveyor. Okay. From here, the die casting process starts. Fume mat, pour metal in, injection, machine open, pig mat go in and pick it up, and press on a trim press. Trim press, trim, the part is dropped into the conveyor system, and we will go all the way to the deburring unit, where it debur, wash, dry, and come out where the packing area here is. They pack, inspect. After that, they bring all the parts over here, where the QC will come and install finished product. TM100 5.5 inch floppy disk drive. You can see on the table here some of our finished products. Some are finished, some are semi-finished. You can see this is the TM100 semi-finished. And this is the TM100 JC 2 cavity. Just now I was saying that there's overflow. These are all written. After trimming, it becomes like that. Inside, actually, we have 3 parts inside. A lever, a module, and a chassis. They bring all the parts over here, where the QC will come and inspect the part, take you out. After inspection, we bring over for shipping, where they check all the parts here ready to go to the vendors for maintenance or whatever it is.
Durch den vermehrten Einsatz automatisierter, kapitalintensiver Druckgießanlagen gewinnt die Forderung nach Erhöhung der produktiven Nutzungsdauer der Gießereianlagen, das heißt kürzeren Umrüstzeiten, zusehends an Bedeutung. Mit gezielten organisatorischen und teils kostengünstigen technischen Maßnahmen kann dieser Forderung entsprochen werden. Dabei dürfen sich die Maßnahmen nicht nur auf den eigentlichen Formenwechsel beschränken, sondern müssen sämtliche Bereiche der Druckgießerei und die gegebenen Rahmenbedingungen, wie zum Beispiel bestehender Werkzeugpark, Platzverhältnisse, Transporteinrichtungen etc. berücksichtigen. Entsprechend der Aufgabenstellung heißt daher die Buhler-Lösung maßgeschneiderte Konstruktionen von einfachen Hilfseinrichtungen bis zum vollautomatischen Produktionswechsel. Das praxisorientierte Beispiel an der GIFA 84, eine kundenspezifische Gesamtlösung für den rationellen Produktionswechsel mit vorgewärmten Formen. Die Detaillösungen der verschiedenen Problemkreise sind formenseitig eine im Schwerpunkt angeordnete Aufhängevorrichtung für den einfachen und sicheren Transport, ein standardisiertes Formentragrollensystem für die exakte und schnelle Positionierung der Form zwischen den Aufspannplatten, außerhalb der Rüstzeit vormontierte Gießkammer mit Zentriereinrichtung. Die formenseitig zu installierenden Verbindungsleitungen sind in der Weise optimiert, dass zum Beispiel alle 4 Kernzugzylinder über einen Zu- und Abgang angeschlossen werden können. Weitere kostengünstige Hilfseinrichtungen sind eine schwenkbare Formhälftenverriegelung bzw. Transportsicherung, die manuellen Schnellkupplungen für die Kernzughydraulik, Temperiermedien und Kühlwasser. Ein standardisiertes Auswerferkupplungssystem, integriert in einen Standardformenuntersatz, der permanent auf der beweglichen Platte der Druckgießmaschine montiert bleibt, ermöglicht mittels je 4 gut zugänglichen Schwenkschrauben die bewegliche Formenplatte und den Auswerfer rationell und in kürzester Zeit zu spannen. Durch maschinenseitig ergonomisch günstige Anordnung der Verbindungsleitungen für die Kernzughydraulik, die Temperiermedien sowie einfachsten Hilfseinrichtungen konnte eine wesentliche Arbeitserleichterung und Zeiteinsparung erreicht werden. Der Produktionswechsel in der Praxis mit heißen Formen, einem Zweimann-Team, guter Organisation und vorgenannter Einrichtungen läuft nun wie folgt ab. Nach Erreichen der vorgegebenen Stückzahlen wird die Anlage auf Einrichtbetrieb geschaltet. Das heißt, sämtliche folgenden Maschinenbewegungen werden mit reduzierter Geschwindigkeit ausgeführt. Die Energieanschlüsse der Form werden entkoppelt. In diesem Falle das Kühlwasser in den maschinen- oder formseitig angebrachten Hilfseinrichtungen versorgt, womit die Kupplungssysteme vor Verschmutzung und Beschädigung gesichert sind und die Anschlussleitungen jederzeit wieder zur Verfügung stehen. Durch die Verwendung von Schwenkschrauben, der Maschine zugeordneten Werkzeuge, möglichst einheitlichen Schlüsselweiten sowie auf das Maschinenaufspannbild angepassten Formplatten wird der Zeitaufwand für das Entspannen der Form auf ein Minimum reduziert. Die Formhälftenverriegelung sowie das Tragrollensystem ermöglichen nun, die komplette Form inklusive Gießkammer mit der Formöffnungsbewegung auf die Entnahmeposition zu fahren. Die vorgängig entspannten Schwenkschrauben des Standardformenuntersatzes werden ausgeschwenkt und die bewegliche Platte auf maximale Öffnungsposition gefahren, womit die Form für die Entnahme nach oben freigestellt ist. Die Vorbereitungen für die neu aufzuspannende Druckgießform, in diesem Falle eine Elektrostatorenform mit allseitig angeordneten Kernzugzylindern, beginnt mit dem automatischen Säulenauszug der oberen zwei Säulen. Dabei werden die Säulen mit je einem Zugzylinder direkt gezogen. Gleichzeitig erfolgt die Anpassung der peripheren Geräte an die neue Produktion, das heißt Wechseln des Sprühkopfes, der Entnahmezange und eventuell des Schöpflöffels sowie der Gießkolbenstange inklusive Stempel. Auch diese Arbeiten sind durch einfache konstruktive Maßnahmen rationalisiert worden. Eine automatische Höhenverstellung für das Einpressaggregat mit integriertem Wegmesssystem erlaubt es nun, die am Steuerschrank neu eingegebene Einpressposition anzufahren. Die mittels Hallenkran direkt von der Vorwärmstation zugeführte heiße Form wird zwischen die Aufspannplatten gefahren. Das in diesem Falle an allen Formen angewandte Rollensystem bedingt, dass in einer vertikalen Zwischenposition die Säulen eingefahren werden und erst danach das Abstützen und somit Vorzentrieren der Form erfolgen kann. Die im Standardsystem vorgesehene Abstützung auf den unteren Säulen wurde hier nicht angewandt, weil das hier gezeigte Rollensystem auch zur Lagerung der Formen dient. Durch die Koppelung der installierten Absaughaube mit der hinteren Schutztürschiene konnte auch diesbezüglich eine einfache, kostengünstige Lösung gefunden werden. In der durch das Rollensystem erreichten positionierten Lage kann nun die Form durch Schließen des Gelenksystems zentriert werden, wobei die Zentrierung und damit das Abheben der Rollen erst kurz vor der endgültigen Plattenberührung erfolgt. Die jetzt folgenden Arbeitsgänge wie Spannen der festen Platte, Ausschwenken der Formentransportsicherung, Koppeln der Auswerfplatte und der beweglichen Formenhälfte mit dem Formenstandarduntersatz können durch die bereits erwähnten konstruktiven Lösungen einfach und schnell durchgeführt werden. Die feste Zuordnung der Formenenergieanschlussleitungen zur Druckgießmaschine und deren ergonomisch günstigen Anordnungen ermöglichen auch diesen Teilbereich des Umrüstens in kürzester Zeit durchzuführen. Nachdem innerhalb von circa 15 Minuten der eigentliche Formenwechsel und das Anpassen der peripheren Einrichtungen abgeschlossen ist, können die bereits erarbeiteten und auf Kassettenband gespeicherten Produktionsdaten der neuen Form eingelesen werden, womit der Umrüstvorgang als Ganzes abgeschlossen ist. Das Hauptmerkmal dieser hier gezeigten kundenspezifischen Buhler-Lösung ist, dass mit einfachen, kostengünstigen Mitteln und einer teilweisen Standardisierung das Umrüsten mit vorgewärmten heißen Formen ermöglicht wird, sowie eine generelle Verkürzung der Umrüstzeit erreicht werden konnte. Produktivitätssteigerung durch Rüstzeitverkürzung, ein Themenkreis, der ganz speziell auf die Gegebenheiten eines Betriebes diskutiert und gelöst werden muss.
Aufbauend auf einem bewährten und in der Praxis bestens eingeführten Maschinenkonzept wurde eine neue Kalkhammerdruckgießmaschine mit einer Zuhaltekraft im Bereich von 11.000 bis 12.000 Kilonewton entwickelt. Maschine, Steuerung, Regel- und Überwachungssystem entsprechen den heutigen modernen Anforderungen in Bezug auf höchste Teilequalität und wirtschaftlicher Produktion, raschem Produktionswechsel, hoher Produktionskonstanz und Verfügbarkeit, bedienungsfreundlichem Arbeitsplatz, hoher Servicefreundlichkeit, hohen Sicherheitsanforderungen. Die kraftübertragenden Bauteile wie Gelenke, Gelenkplatte, Säulen, feste und bewegliche Aufspannplatte sind hinsichtlich Bauteilfestigkeit mit modernsten Mitteln optimal gestaltet worden und tragen somit zu einer hohen Betriebssicherheit und langer Lebensdauer bei. Den heutigen strengen Sicherheitsvorschriften wird durch umfangreiche Sicherheitseinrichtungen Rechnung getragen. Es sind dies obere und seitliche Schutzgitter für den Gelenkbereich, pneumatisch betätigte Schutztüren für den Formbereich. Das gewählte Konzept von Formbauhöhenverstellung, hydraulischer Säulenklemmung und hydraulisch betätigten zweiteiligen Säulenmuttern auf der festen Aufspannplatte ermöglicht das rasche, vollautomatische Aus- und Einfahren einer oder beider oberen Säulen. Diese Einrichtung verkürzt die Einrichtzeiten wesentlich, da bei einem Formenwechsel das Säulenziehen bisher den größten Anteil an Zeit beanspruchte. Nicht zuletzt wird dadurch die erhebliche Unfallgefahr, welche bei der Demontage und Montage der vorderen, meist extrem schweren Säulenmuttern bestand, ausgeschaltet. Für extrem unsymmetrische Formen ist eine Einzeljustierung der Säulenvorspannung über die hinteren Säulenmuttern nach wie vor in gewissen Grenzen möglich. Ganz allgemein zeichnet sich die Maschinenhydraulik durch ihren einfachen Aufbau, Übersichtlichkeit und Servicefreundlichkeit aus und trägt damit wesentlich zu einem hohen Zuverlässigkeitsgrad und somit kurzen Stillstandszeiten bei. Selbstverständlich ist die hydraulische Anlage für den Betrieb mit Hydraulikflüssigkeiten des Typs HFC ausgelegt. Die von Grund auf neu konzipierte horizontale Kalkhammergießeinheit ist durch folgende Details gekennzeichnet. Kurze, kompakte Konstruktion mit Blockhydraulik und vertikal angeordnetem Multiplikator. Gießzylinder in massivem Führungsrahmen abgestützt. Ein gießteilseitiger Ausbau der Gießkammer ist ohne Demontage der festen Formhälfte möglich. Schnellkupplung für die Gießkolbenstange, Wegmesssystem für die Überwachung der Gießkolbenbewegung. Primär druckgeregeltes Multiplikatorsystem mit separater, unabhängiger Druckspeichereinheit. Das heißt, die gewünschte Nachdruckhöhe wird durch entsprechende Regelung des Gasdruckes auf der Primärseite des Multiplikators erreicht.
extreme Leichtbauweise des Multiplikatorkolbens für schnellen und überschwingfreien Druckaufbau. Heutige komplexe Druckgießanlagen verlangen nach Steuerungen, mit denen nicht nur Maschine und Anlage, sondern auch der Druckgießprozess gesteuert und überwacht werden kann. Solche Steuerungen müssen sich durch höchste Zuverlässigkeit, Sicherheit, Bedienungsfreundlichkeit und laufende Überwachung mit Fehlerdiagnose auszeichnen. Das neu entwickelte CNC-Steuer-, Regel- und Überwachungssystem besteht im Wesentlichen aus zwei Hauptteilen, nämlich der eigentlichen Steuerung Datacess mit dazugehöriger Steuersäule für Maschine- und Peripheriegeräte, dem Mess- und Überwachungssystem Prozessroll für den Gießprozess. Die Kombination von Bedienungstastatur, Bildschirm sowie der Steuerungsintelligenz ermöglicht einen einfachen Dialog zwischen Bediener und System. Bedienung, Kontrolle und Überwachung werden unterstützt durch geführtes Einrichten, Plausibilitätskontrolle der Eingabedaten, Fehleranzeige im Klartext mit Behebungshinweis. Mit der neuen Druckgießmaschine wird dem Druckgießer eine moderne Maschine mit neuem Gießaggregat mit hoher Einpressleistung zur Verfügung gestellt. Das neue CNC, Steuer-, Regel- und Überwachungssystem Datacess und Prozessroll trägt zur besseren Prozessführung, hoher Sicherheit und Bedienungsfreundlichkeit bei.
Let us follow a test casting cycle of Stator 112 in our Uxville laboratory, carried out on an H630B die casting machine. The fill mat unit ladles the correct quantity of molten metal into the shot sleeve, and the shot is immediately released. With the core pull units closed, the runner is separated in the first ejection stage. In the second stage, the stator and the runner are ejected from the die. The die is carefully blown out and sprayed. The standard proven alloy used for the stators as well as the bearing plates is AlSi8Cu3. Depending on the size of the casting, this method allows production rates of between 24 and 60 shots per hour. The exchangeable slide cores for foot-mounted or flanged motor housings have been deliberately arranged at the top of the die. This allows the slide core to be quickly and easily changed when switching production to the flanged version. By casting separate housings instead of casting the metal around the stators, larger production lots are possible, since all the castings are identical and independent of the later polarity of the stator laminations. At the end of a production cycle, the die can be changed while it's still hot, thanks to a number of quick production change features. Less time is required to change dies, thanks to the following features. Easy access to the clamping bolts with standardized spanner openings. And color-marked quick-action couplings for the heating and cooling systems of the die. The die is changed along with the anchored shot sleeve. To install wide dies, the top tie bars can be automatically withdrawn. Die support rollers and gravity-centered suspension gear make die changes very much easier. All of the dies used can be coupled to the machine-integrated base. The next die for bearing plates, already preheated, can now pass between the tie bars, centering itself by means of its support rollers. Hinged bolts and latches at the partition line allow production to be continued after a short time. The die design makes provision for automatic stator extraction by means of a pick mat handling unit. The method of casting housings favors automation, as the weights to be handled are less than 15 kilograms. The design and manufacture of the dies for the 9 different stator sizes are all based on the same principle. Bearing plates. The various bearing plates are further components of the electric motors manufactured by the die casting process. The bearing plates at the drive end and at the non-drive end. And the flanged bearing plates form 3 die families. The features of our quick die change system, in addition to machine-integrated die platens and the fact that the same die base is used as for the stators, allows productivity to be improved considerably. Thanks to the fact that the central runner has flow paths of identical length, ideal air displacement conditions, and thus sound castings are obtained. The low trimming requirements reduce subsequent metal cutting. Let us now follow a trial casting with flanged bearing plate die 132. The production rate is between 50 and 90 shots per hour. Castings of different sizes are produced on machines with locking forces of 2,500, 4,000, and 6,300 kilonewton. When the die opens, the middle plate is restrained by a stop, causing the central runner to be separated. The biscuit drops out of the partition between the gate and the plunger when the plunger retracts. Here, too, provision has been made for fully automatic production, featuring spraying units, mandrel extractors, and extraction of the castings by a pick mat handling unit. Rotors. Production of 2, 4, 6, and 8 pole rotors is performed by 2 die casting systems in this project. With shaft heights of 56 to 90 millimeters, 2 impression dies are used, and the locking force is 2,500 kilonewton. With shaft heights of 100 to 160 millimeters, single impression dies are used, and the locking force is 4,000 kilonewton. Let us now watch our biggest system in operation at our research department in Utsville. The laminations are stacked onto mandrels in a secondary operation carried out simultaneously with the die casting cycle. The height of the lamination stack is digitally measured under a pressure of 100 kilonewton and corrected if necessary. Then the top lamination is clamped and the lamination stack is forwarded to the die casting machine on a stepping conveyor. The operator of the die casting machine grips the lamination stack to be cast, and the stack is turned 90 degrees for loading into the die. Die spraying and cleaning are effected even before the stack is transferred to the die. When the lamination stack has been loaded, the casting cycle is immediately started. In a simultaneous secondary operation, the mandrel is ejected and at the same time, the runner is trimmed off the rotor which has just been cast. The press table tilts 90 degrees, transferring the finished rotor to the discharge ramp. In the meantime, the die casting cycle has finished. A new rotor is taken and placed vertically into the mandrel press. The loading operation begins anew. Spraying of the two die halves. Loading of the lamination stacks. Conveying of the molten metal by fill mat. And when the die is closed, ladling of the molten metal into the machine and shot. The production rate here is 26 to 55 shots per hour, with different size castings being produced. An electric heating system in the die and a controlled die venting system contribute to good quality castings. Both are products of our long years of experience. The cooled mandrels, of which 10 are in circulation for each type of housing, are returned to the stacking station by a belt conveyor. Quick switching of production to another rotor type is accomplished by exchanging the middle die plate together with the movable cavity for the short-circuiting ring. The modular rotor die system, too, is provided with quick production change features, including lugs, hinged bolts, etc. Then the venting unit can be retracted. The change plate is released, resting on its support rollers, and is now ready to be lifted out by the hoist. A new middle plate is lowered in, centered by means of its support rollers, and clamped. Using an auxiliary device, the fixed die cavity is exchanged. The shot sleeve, too, can be changed hydraulically. Finally, the plunger rod is installed. A new production cycle begins when the mandrel and lamination stacking presses have been reset by the operator at the stacking machine. Our long years of experience in the manufacture of die casting systems Automatic die casting system for production of small rotors. Buhler presents a fully automatic die casting system for the production of small rotors for electric motors, featuring a two-cavity die and an edge gating system. The total system produces rotors with temporary mandrels and permanent shafts. The edge gating system was selected because only small lots are produced, but in a large variety of different types. The system is designed for casting rotors with different diameters, ranging from 55 on up to 110 millimeters, and lamination stack heights from 25 to 140 millimeters. It allows production of a total of 160 different rotor types. For this reason, the entire system has been designed for quick and simple production changes. The lamination stacks are manually loaded into the singling station. There they roll via flip-flop system to the bottom and the top loading stations. A limit switch signals the end position. A pick mat, pick and place handling unit, grips two stacks simultaneously and moves them vertically to the top end position. This position is identical for all the different rotor diameters. Insertion of the lamination stacks, extraction of the cast rotors, and die spraying are all done at the same time. During spraying of the fixed die half, the rotors are extracted from the movable die half. When the lamination stacks are inserted in the fixed die half, the movable die half is sprayed. The cast rotors are placed onto the lower part of the trimming die. The sliding table then moves into the trimming press. When the press closes, first the mandrel is ejected, and then the gating is trimmed off. A special cylinder makes sure that the gating is extracted. An additional dropout detector is also provided. The new cycle is only started if the system has been cleared. In other words, when the gating has left the system. After opening the press up to the intermediate stop, the sliding table moves to the pick mat loading position, and the rotors are pushed onto a horizontal plate. When the sliding table returns, the rotors are pushed into a separate channel by means of a deflection plate, from where they're taken for further processing. The lamination stacks are mounted on a mandrel or on a finished shaft. The largest rotors, with 110 millimeters diameter, weigh 7.5 kilograms. That's equal to 16.5 pounds, the mandrels included. Simple production changes on the system are of crucial importance to overall economy. Production changeover times must be minimized. These are the exchangeable parts of the singling station, the pick mat gripper, as well as the interchangeable inserts of the trimming die. The die design is such that, for instance, when there are die inserts in the movable die half, only the inner bushings have to be changed. the exchangeable components can already be prepared while production is still going on. In other words, in parallel to the production process. The bushings are split. The new inserts with adapter rings and the bumper pins are installed in shell halves. Then the other shell halves are fixed in position, resulting in a compact unit. The exchangeable parts of the peripheral devices can quickly and easily be installed. Change the lamination stack stops. Adjust the feed track to the new stack height. Change the prism of the pit mat gripper tongue. Adjust the vertical height stop of the pit mat unit. Change the lower part of the trimming die. Change the top part of the trimming die. When changing the die inserts, the two bushings are first ejected, then removed by a manipulating device and deposited. The new inserts, which have been prepared in advance, are then placed onto the manipulating device and moved into the die. Here, the largest rotor type is being cast. With this rotor type, a cycle time of approximately 45 seconds was achieved at our laboratory. After startup at the customer's foundry, the cycle time no doubt will be even shorter. As with most of our customer projects, this complete production system underwent production trials at our own testing facilities. These excellent results were achieved thanks to good cooperation between the customer and Buhler from the very first contacts up to the final acceptance test by the customer. The automation of such die casting systems results in productivity gains quite often exceeding 50%, and in addition, in improved working conditions for the operator. In this short film sequence, we would like to show you a die casting system for external rotors of electric motors. A number of such systems have already been built by Buhler in various designs, with 6 impression and 8 impression dies, and for rotor diameters of 70 and 90 millimeters. The cast rotors are removed by means of an extraction device at the rear of the machine and deposited. The cycle time achieved translates into 80 shots per hour. In other words, 480 rotors are produced each hour. The inserts required here for each cycle comprise 6 lamination stacks and 6 centrally arranged bearing bushes. This is how the inserts are picked up from the singling station by the loading unit fitted to the front of the machine and transferred to the die. Based on many years of experience in this field, the Buhler company has been able to achieve an extremely high degree of automation for such production systems. Our team of experts stands ready for the design of entire die casting systems or even complete foundries. All equipment so far delivered to customers around the world proves the high quality and day-to-day economy of Buhler systems.
Our aids could no longer be imagined without die castings. They service in many everyday products, sometimes without our noticing them. Die casting technology has evolved at a breathtaking pace, and Buhler Miag, has been active in this field from the very beginning, contributing considerably to the development of modern die casting machines and plants. Die casting with Buhler. The die casting process allows large series of non-ferrous components to be produced with great accuracy and very economically. In the process, molten metal is fed into the shot sleeve of the die casting machine and squeezed by the plunger into the die cavity. The liquid metal fills the die, duplicating the most minor details of the cavity. Even very complex and thin-walled parts can be produced by the die casting process. Suitable metals include aluminum alloys, zinc alloys, magnesium alloys, and copper alloys. To enable die castings to be produced efficiently, Buhler designs, builds, and supplies die casting machines with locking forces of up to 20,000 kilonewtons. The manufacture of our machines, for instance of this 10,000 kilograms stress platen, is carried out by the most up-to-date methods on numerically controlled machine tools. The individual sub-assemblies such as base plates, stress platens, die platens, and shot units are separately pre-assembled in series by specialists, then tested, and finally assembled into the finished die casting machines. This, for example, is a machine with a locking force of 20,000 kilonewtons. In a separate Buhler production facility, we build the electronic control systems for our machines according to state-of-the-art methods. Routine inspections of the individual components rule out potential sources of failure at an early stage. A subsequent test of the entire control system according to strict specifications ensures dependability later on. The logical and clear layout makes for quick and reproducible setting up of the machine. The display of the major functions and faults allows the status of operation to be checked at any time. The freely programmable Diecast control system permits optimum adjustment to the current requirements and great ease of operation. To ensure an immediate production start at the customer's plant, Each single machine is put through its paces in an 8-day trial run at our works. The acceptance test, featuring over 1,000 checkpoints, is recorded, and the record is delivered to the customer along with the machine. Here, the expansion of the tie bars is being measured by the so-called strain gauge test. And here, the shot unit is being accurately aligned by means of an optical alignment instrument. Finally, each machine is subjected, together with the control system, to a 100-hour endurance test at maximum load to eliminate potential sources of failure. After painting, the die casting machines leave our works to be shipped throughout the world. The machines are started up at our customers' plants by Buhler specialists to ensure a quick and dependable production start. For the automation of the die casting process, Buhler offers the Filmat and Picmat handling units. The Filmat metal labeling device ensures that an accurately proportioned quantity of molten metal is fed to the die casting machine. For the extraction of the castings from the machine, our simple Picmat unit has proved to be of great advantage. It operates with short cycles and allows accurate positioning of the die castings. The Picmat unit is also suitable for positioning parts into the die that will be integrated in the casting. Before the 4-impression casting is extracted, the tongs grip the bearing bushes and place them into the die cavities. Here, pump housings for washing machines are being cast. Our experience in automating die casting operations has led to the development of a modular production system called Module Mat. The link-up of the die casting machine with the peripheral devices allows fully automatic trimming of the castings next to the die casting machine. But Buhler offers more than just die casting machines and plants. We also offer you comprehensive expertise, for instance in selecting the correct die design. The most up-to-date machine tools permit efficient construction of dies. The dies designed by us are tested and supplied, ready for use to customers all over the world. To ensure rapid production changes, Buhler die casting machines can be equipped with a quick change system. The automatic tie bar withdrawal device, for instance, reduces downtime and makes setting up easier. Our own die casting plant is equipped with 34 machines, producing castings for the Swiss market. This enables us to build machines and plants which will meet the tough conditions encountered in practice. To achieve perfect casting quality, we have various testing procedures at our disposal. Spectral analysis permits changes in the alloy to be detected on a continuous basis. Porous sections in the structure of a casting become visible in the X-ray test. Purity is analyzed under the microscope. Our metallurgists and their modern testing equipment are also at the disposal of our customers. The design and construction of plants and special installations is carried out by a team of specialists. We stage regular courses on hydraulics, electronics, technology, and machine setting up for training our customers' personnel, making them familiar with our machines and plants. The worldwide Buhler after-sales service network guarantees prompt delivery of spare parts and quick dispatch of our specialists on site to minimize plant downtime. Taking a few plants as examples, we would like to show you how Buhler die casting machines are used by our customers. This, for instance, is a plant for the automatic production of carriers for bicycles. The shot weight is 0.6 kilogram with 120 shots per hour. After trimming, the castings are polished and assembled into carriers. This fully automatic plant featuring a fill mat and pick mat unit produces 360 hot plate elements per hour. Our die casting machines are mainly applied in the automobile industry. This cold chamber machine with a locking force of 20,000 kilonewtons turns out 20 engine blocks per hour with a shot weight of 30 kilograms. Thanks to advanced die casting technology, it is possible to manufacture even such complicated parts efficiently and with great precision. Another automobile factory applies our machines for producing a wide variety of castings. This Buhler cold chamber die casting machine with 6,300 kilonewtons locking force produces cylinder head covers for car engines. Here too, the quality of the castings will greatly influence the dependability of the finished product. This is why many renowned automobile manufacturers rely on Buhler. You too should trust Buhler when it comes to die casting. For we offer you high quality equipment, advice in die design, total problem solutions, single source responsibility, constant further development and research. Our own die-casting shop. Worldwide after-sales service network. And not least important, long years of experience in designing and building die-casting machines and plants. The control system of the module mat production unit, which is independent of the die casting machine, is freely programmable and offers maximum flexibility and operating convenience. It ensures central control and monitoring of the extraction unit and the trimming press. Signal lights allow the automatic production process to be supervised at any time. The die casting process can be automated step by step by adding peripheral equipment such as the fill mat unit for automatic metal ladling, the pick mat unit for parts extraction, and the automatic die spraying unit. These devices have become common and proven equipment in die casting foundries. The module mat concept is the consequence of further developing the automation idea, integrating the finished operations in the immediate die casting area. The accurate positioning of the casting extracted by the pick mat unit allows the part to be placed direct on the sliding table in its correct position. The cooling station with its thermostatically regulated cooling circuit ensures uniform cooling and thus optimum trimming conditions. Besides cooling, the flexible spray nozzles also clean off metal chips from the trimming tool, ensuring trouble-free operation. The horizontal position of the sliding table and trimming tool ensures ease of accessibility, reducing setup times and allowing good, safe visual control of operation at all times. The trimmings and the castings are discharged separately. The castings being held by the movable trimming tool and ejected onto a tilting plate by a hydraulic ejector. Besides accurate trimming, the module mat system also allows further machining operations in the trimming tool while the die casting process is going on, so that additional machining operations can be completely or partially done away with. The die casting machine and the trimming press are autonomous system components, enabling them to be operated separately if required, which ensures a high degree of capacity utilization. The space-saving compact design, the possibility of running with cold and hot chamber machines, and a high degree of flexibility are further outstanding features.
With the pair-shot injection system, Buhler has reached a new milestone in die casting technique. In our research laboratory, extensive filling trials were carried out, which were recorded with a high-speed camera making 6,000 exposures per second. The time-distance diagram of the conventional injection system shows the characteristic slow approach movement with constant speed during the first phase. The linear movement causes a disturbing turbulence within the sleeve. With the filling procedure of the injection system, as it is generally practiced nowadays, a wave is formed at the beginning of the injection movement, which breaks away from the plunger, hits a wall at the end of the sleeve, and closes the gate area. The enclosed air cannot escape anymore and mingles with the liquid metal. The resulting porosity has a disadvantageous influence on the quality of the casting. The actual picture of the plexiglass sleeve with tinted water, taken in slow motion, shows the turbulent flow with the three-phase injection system. In the repetition of the trick film, once again you can clearly see the disadvantages of the conventional system. The time-distance diagram of our new injection system is characteristic for the parabolic, constantly accelerated injection movement during the slow approach phase. The parabola is distinguished by our trademark parashot. With the constantly accelerated injection, the filling proceeds absolutely calm. The metal slowly builds up before the plunger, and there is no wave that breaks away. The gate area remains unobscured. A complete volume of air can escape and does not mix with the liquid metal in the sleeve. At the plexiglass model, the calm filling of the sleeve can be clearly seen. Since there is no precipitous wave with the parachute system, the filling is free of turbulence. This results in a homogeneous structure and minimum dispersion of the strength values in the castings. With the development of the new injection system parachute, the problems arising from gas enclosures in the filling sleeve are eliminated. Some very promising aspects of this system will bring about many advantages for the die caster concerning quality, optimum surface finish, homogeneous structure, minimum dispersion of strength values, higher filling ratio, and, as a result, economical production of die castings.
Buhler Miyag presents automatic die casting of rotors and stators. In October 1976, we were asked by Watt Electromechanic, a licensee of Brown Boveri Limited, to design and build a die casting foundry in Istanbul. This foundry was to produce all the aluminium parts for a new electric motor series. The plant is designed for a yearly capacity of approximately 190,000 asynchronous motors having shaft heights of 63 to 225 millimeters. We supplied the following equipment. The equipment for the central melting house, the liquid metal conveying system, and the holding furnaces. All the die casting machines, including 45 dies, ladling devices, die spray devices, and other equipment. The emphasis, however, lay on the two custom-made manufacturing systems for stators and rotors, whose functional principles we will now look at more closely. The rotor die casting facility consists of die casting machine, twin chamber furnace for pure aluminium, ladling device, loading and unloading ramps, stacking machine for rotor lamellae, mandrel removal station, die change device, die assembly device, and the electronic controls. The facility was completely assembled at our works in Utsville for testing and final approval. The following shots were taken during these first tests. From stacking to deburring the rotors and pressing out the mandrels, the facility carries out all the necessary process steps. The heart of the system is the die casting machine with 6,600 kilonewtons locking force. The Filmat ladling unit by Buhler feeds the liquid aluminium into the die casting machine. The required amount of metal is taken at an accuracy of plus or minus 1% and transferred to the pouring hole. The rotors consist of individual lamellae, whose slots are filled with metal in the die casting machine. The stack height is measured under pressure and, if necessary, corrected in accordance with the digitally displayed result. As soon as the correct height tolerance has been reached, the go-ahead is given for transfer to the swivel manipulator. It deposits the laminar stack onto the inclined loading ramp, and the stack rolls onto the buffer zone. The front stack is singled out and reaches the loading prism. It is then pushed through the fixed machine platen
into the moving die half. On completion of this motion, the machine closes and is ready for casting. The valve of the ladling device opens. The molten metal flows into the filling sleeve and is instantly injected into the die. This diagram shows the filling process of the die, during which the Buhler die vent control system prevents the occlusion of air in the casting. Here, the displaced air escapes through the vent valve. On solidification, the rotor is returned to the loading station. The ejection stroke through the trimming die removes the runner, and the transport rod carries the rotor back to the prism. The radial thrust motion causes the rotor to roll away on the inclined discharge ramp. A new cycle is initiated by loading a laminar stack into the die. The runner of the previously cast rotor is ejected. This facility is capable of turning out 40 rotors of the largest type every hour. The shot capacity lies between 2 and 8 kilograms, depending on the rotor size. The rotor diameters are between 100 and 250 millimeters, and the possible stack heights range from 100 to 315 millimeters. This is a rotor rolling into the mandrel removal station. The individual rotors leave the buffer zone and enter the clamping device, where a horizontal ram presses out the mandrel. The mandrels pass through a cooling area and complete their cycle. The finished rotor can now be forwarded for further processing. Thanks to the electronic process control system, as well as to the equipment for rapid die change and the modular die system, minimum downtime and a high degree of efficiency are achieved. The hydraulic change system also makes it possible to exchange the filling sleeve in minimum time. For changing dies, the two die halves are connected with a few operations. After hydraulically loosening the locking wedges, the die is separated from the moving platen. The pull rod is coupled with the die to be exchanged. The die, which is still hot, may easily be drawn into the working range of the hoist. On the other hand, a preheated die can be quickly installed in the die casting machine. All these provisions allow flexible production in small series of this plant's 44 different rotor types. An expensive stock of semi-finished products thus becomes largely unnecessary. During production of a certain series, the next modular die is already being prepared in the die service section. The mechanical die assembly device permits quick and reliable assembly and dismantling of the components, while gently handling the dies. The quality of the rotors is distinguished by non-porous casting, thus meeting the requirements of electrical equipment. This facility for the fully automated production of stators consists of die casting machine, electrical holding furnace, ladling device, manipulator gantry, stacking machine with circulation conveyor, gravity conveyor for stators, and the controls. This is the actual facility assembled for the first casting tests at our work. The vital element of the system is the die casting machine with 15,000 kilonewtons locking force. The process includes the preparation of the laminar stacks and the casting of the stator housing. In the pre-stacking station, the stator lamellae are stacked by hand on positioning plates and then checked under pressure for proper height in the stacking machine. As soon as the digitally displayed tolerance has been reached, the gravity conveyor carries the stack to the heating station. The laminar stacks are individually lifted into the induction coil for heating, and on attaining the required temperature, are transferred to the swivel manipulator located above. The stack is switched 90 degrees into a horizontal position.